We're given the following circuit diagram. We are also told that the sinusoidal voltage in the circuit is developing a voltage equal to this. So our V of G right here is going to be 247.49 with an angle of 45 degrees. We need to find the Thevenin voltage with respect to terminals A and B. We need to find the Thevenin impedance also. So we're going to find the Thevenin voltage first, but at the same time when we're doing source transformation, we will be changing our impedances so that we will sort of be getting into a formula so that we can find our Z A of B. To start this off, what I'm going to do is look at this part right here. So I'm going to change this from a voltage and impedance in series to a current and impedance in parallel. We can do this with source transformation. This can be found in section 9.7 of the notes linked below the like button. So this is what our new diagram will look like. From here, I'm going to do a couple of things. First, we need to find our I of G. Well, we know that our I of G is going to be equal to the V of G divided by our resistance of G, and this is Ohm's law. So we're going to set 247.49 with our angle of 45 over our 100 milliohms. However, we can't just have this over 100 milliohms. We need to convert this using the Z of L method. And the Z of L is going to be our J times our omega times the inductance. This formula is also in the notes with an explanation of it. We know our omega to be 1000. So we are going to have 1000 times 100. And since we're dealing with millis, we want to put it in just henries. So we're going to multiply this by 10 to the negative 3. And this is going to give us a Z of L with J times 100. So all of this up here is going to be over a J times 100. Now we need to divide this out. And to divide this out, I need to convert the top part from polar form to rectangular form so I can divide in the J over 100. The formula to do this is that we're going to take our number and then we're going to multiply it by the parenthesis. And inside of our parenthesis, we have the cosine of our angle plus J times the sine of our angle. And if we do this, we are going to get this equation. From here, I'm just going to divide in our J. So we're going to get that our current, I of G, is equal to 1.75 minus J times 1.75. And now we know the current flowing through the leftmost side of our diagram. Next, I'm going to look at our impedances. Our impedances, all of these three, are in parallel. So what we can use is use the parallel formula and combine them together. However, we need to convert them just as we did with this part right here. So to convert these, we know that this 100 millihenry is already going to be J times 100. And then we have to add these two together since they are in series. First, we are going to convert this 100 millihenries, and it's going to be the same for this impedance up here. We know it's J 100. So we're just going to have 100 plus J times 100. Next, we need to convert this 10 microfarads. And the formula for this, I'm going to do it over here, is that we're going to have our Z of C equal to a negative J over our omega times C. So when we plug this into a calculator, we're going to have negative 1 divided by 1000 times 10. And since this is micro, we want it just in farads, we're going to multiply it by 10 to the negative 6th. All that's in the denominator. And we are going to get a negative J times 100. And we are now going to write all of these in the parallel formula. This is the parallel formula for our impedances. And we can see that we have a negative of this here and a positive of this here. So we can just cancel them out. Now with the very last part, we flip it over. So we're just going to have a 100 plus J times 100. And while we found our impedance here, so we can rewrite this, and this is going to be our 100 plus J times 100, and this is at our terminals A and terminals B. And again, we've found our Thevenin impedance, so we can just plug it into right here. But we want it in polar form. The question asks us for the magnitude and degrees. So to convert this to polar form, we are going to use the following equation, where we have our Vmax equal to the square root of our real number squared plus our imaginary number squared, and our theta equal to tangent negative 1 of our imaginary number over our real number. And if we do that, we're going to get approximately 141.4 with an angle of 45 degrees. And that is the polar form for the Thevenin impedance. Now we need to find the Thevenin voltage. And to find the Thevenin voltage, we are just going to convert this part back to voltage and then a impedance in series. So we're going to say that our voltage of G we know is equal to our V A of B, which is also equal to our V T of H, which is what we want to find. And this is going to be equal to our I of G times the impedance. I'm just going to write R of T of H since it's the entire thing. Now we are just going to multiply these together. We found our I of G up here, which we are going to plug in. We have a 1.75 minus J times 1.75, and this is being multiplied by our 100 plus J times 100. Now I'm going to factor these and add them together. And from this, we are going to get 350 plus 0J as our imaginary number. And if we convert this back into the polar form, which is what we want, again, using these equations down here, we are going to get 350 for our V max, and then we are going to get an angle of 0 degrees. And that is how you would go about solving this problem. If you have questions about the material we covered, you can leave them in the comments below. If you want more network analysis problems or notes covering this entire material, they will be linked below the like button in the description.